Okay, it's 12 o'clock. We'll go ahead and get started with our SAE Lunch and Learn. Hello, everyone. My name is Ted Arnold. I serve as the Vice Chairman for the SAE Atlanta chapter in the state of Georgia. I'll be the MC for today's event. I want to welcome all of you to today's Lunch and Learn with RDI Technologies. This webinar will be recorded and placed on our website at www.saeatlanta.org for future reference. Before we get started, though, I have a couple of other members of our SAE Atlanta team I would like to introduce. First of all, Heather Woods. Heather is the Vice Chairman at our SAE Atlanta chapter over the state of Alabama. And I'd also like to recognize Mike Stonecipher, who is our Chairman. And Mike has been with the SAE Atlanta chapter for many years, serving in this capacity, works very hard and has really been instrumental in growing our team. So welcome both Heather and Mike. I'd also like to tell you just a little bit about the SAE Atlanta. We are part of the SAE International, and SAE International has over 138,000 global members. In addition to its standardization efforts, SAE International devotes resources to projects and programs in STEM education, professional certifications, and also collegiate design competitions. So with that being said, also SAE section has over 700 members, the SAE Atlanta section, excuse me. We promote events and webinars such as this Lunch and Learn. We also support STEM education through the AWIM, which stands for A World in Motion, and provide support for students and SAE competitions. If you'd like to become a member of our SAE Atlanta group, you can visit our website at saeatlanta.org and look for the membership page. Professional membership is $120 a year, and student membership is $35 a year. All right, now that I got that housekeeping out of the way, we're here today with our Lunch and Learn with RDI Technologies. I want to introduce Dr. Jeff Hay. Jeff is the founder and CEO of RDI Technologies. He is the inventor and visionary behind motion application and the Iris-M, which allows you to amplify and measure motion with the use of video. His products are moving industrial vibration to the visual spectrum. His passion is using his background in applied optical technology to change the way you see and measure motion in industrial applications. Jeff, we're thrilled to have you with us today and very excited to hear about RDI. So with that being said, I'm going to kick it off to you.
Thanks, Ted. I'm going to go ahead and grab the screen here and put my presentation up if that's okay. Okay, hopefully everybody can see that. Thanks for that introduction. So the topic today we're going to be talking about is motion amplification. That's a technology that is a camera-based technology that we've developed for measuring motion and vibration. And we'll do a short introduction here, and then we'll talk about some applications and some case studies. But I would also really encourage you to ask questions as well. You know, this is a new technology that I'm guessing a lot of people in the audience hasn't been exposed to. And so if you have any questions along the way about what you're seeing or anything about the technology, feel free to put those in chat, and we'll be happy to get to those and answer those. The presentation's pretty video focused. And so you'll see a lot of videos in here. If for some reason those videos don't play smoothly, it's likely the bandwidth. So it's my understanding this will be recorded and shared later. So there's always that chance to catch those videos later. But I just wanted to put that out there so everybody knows. Okay, so just a little bit about me. I'm the CEO of RDI Technologies. My background is in physics, applied optical physics, but it's got to start with astronomy of all things. I mean, I think people, when people generally hear that, it sounds like they're very far off in what we do now with compared to astronomy, but they're actually pretty related in the sense that really what we're doing is using a camera to measure motion and measure things at a distance. So in one case, it happens to be a star that is light years away. In another case, it might happen to be a product or an asset on the factory floor that you're wanting to understand. In both cases, all you have is the camera to be able to be able to make any sort of inferences about that object that you can. So this work originally started with DoD and DHS, and then it's evolved. So they were interested in terms of the research for remote observation and surveillance. And then it's found its way into the industrial world through asset condition management and monitoring. So just a really quick, a little bit about RDI Technologies. We are, the inventor of the technology. We come with a pretty extensive vibration background in terms of industrial solutions. You can kind of see the systems there that we use to be able to measure this motion. The IRIS-M, it's like a troubleshooting kit. The MX is a high-speed version of it that can see faster things. Also note the CM too. So you sort of have the IRIS-M you can use this as a point-in-time kind of troubleshooting tool. But also note with the examples that you see here, there also is the capability of recording and measuring these things continuously 24/7. So that's one thing to keep in mind. And so we've been really excited about the adoption of the technology. Pretty much spans, any industry from power generation to data storage. You can kind of see there. Okay, so let's go ahead and get into it. What is motion amplification, right? So, well, you're going to see some videos here. Sometimes you'll see a single video. Sometimes you'll see a side-by-side. The left is an actual real video. The right is a motion amplified video. That's really what that engine is doing, and so we'll loop this and you'll see, but this is an engine startup, right? So on the left-hand side, again, that's what you see with your eye. You open the hood, everybody's opened the hood of their car and they've watched it start up, right? You can actually see some of the fuel lines start to vibrate there right before this engine kicks on. And you can see it go into the startup and then now it reaches a steady state. But the idea is what we're doing is full field vibration. We're measuring displacement across the entire field of view, pixel to pixel. And then once we can measure that displacement, we're able to visualize it, increase that to a point that it's visible by the naked eye. So let's look at a couple, everyday objects. This is a glockenspiel. I call it a xylophone, but my son's in band and he informs me that is a glockenspiel, and not just a xylophone. So in this situation, you can actually see the key vibrate here. I think we'll pause there for a second. You can actually see the key vibrate, and you wouldn't normally be able to see that with your eye. That's actually 1,170 hertz. So not only is it extremely small motion, but it's extremely fast motion. And then maybe just another everyday object here. This is a wine glass, right? So that's a wine glass like at 750 hertz, just oscillating just from a single tap with a spoon, so you just kind of tap it. So just an idea of what we're talking about, but really in terms of technology, what we're trying to do is turn every single every single pixel into a displacement sensor. So in a nutshell, what you're doing is you're able to measure the vibration across the entire field of view. So let's take, for example, the scenario of a megapixel camera, right? That's 1 million pixels, and that's sort of a modest camera even. But if you think about each pixel now being a displacement sensor, now you're able to cover the entire field of view with millions of sensors. In an HD camera, that's 2.3 megapixels. That's 2.3 million sensors you've got all over that structure that you're able to move, and you're able to measure the movement of. And so you can actually do that, and you can actually measure it. You can see it in these examples. We're showing you the visualization, but you can see it. And so in this case, we've got this spectrum up here, right? You see this spectrum at the top, and that's what that is a frequency spectrum that tells you what frequencies of motion are present in that and how much are present in your asset, right? And maybe to a trained eye, that becomes a useful piece of information, right? And they've got to determine what that fault is. But with the visualization tool, you don't have to really get to that point. You can actually understand what the fault is. You can see it in the visualization, and so that helps in the case of a communication piece, which I'll talk about throughout this presentation. Okay, let me see. I lost my chat window here. I'm monitoring the. Try to get that back up. Okay. Okay, great. I got the chat window. I didn't want to miss any questions. So, okay. So let's keep going here. Okay, so talked about this idea of full field vibration, right? So this would be maybe a traditional way of measuring an asset. You've got this motor and this pump here. You might have some contact sensors on it. With motion amplification, again, it becomes that full field vibration. You're not a single point is being left untouched with the measurement. So let me show you a short video that kind of hits that home here. So this is the idea that maybe if you had a single data point, you would be measuring that, or two data points, you might be measuring this, right? But imagine if the entire asset were covered in measurement locations, you would see something like this. And this is what you would be missing, right? You would get a high vibration, or you measure some motion, and you would see that, but you might not have any idea that this is going on with your asset or your test cell or your product that you're designing, because you're not seeing the full picture. So just talking a little bit about the benefits. One is the ease of use. This gets a lot of so when users of the technology really benefit from the idea that it's more like a GoPro taking video than it is about collecting data. Really, it's you sit down, and I'll do a live demonstration. You sit down and you show. You set up your focus, the lighting, you get that right, and then you're ready to take the data. So it really is more akin to taking video than it is to taking data, which I think is more intuitive for most people. So the non-contact and non-destructive. So those in the automotive industry know that there's lots of times that there's light curtains, things like that you might not be able to get behind. There's barriers to entry. There's areas you can't go in. That becomes problematic. And then of course it's non-destructive. So there's no surface preparation, nothing that you have to put on the object. You literally, can stand at a distance and do everything you need to collect all the data that you need. And then also just scaling, right? When you go from 1, 2, 3 to a dozen sensors, it becomes very time consuming to add those sensors to the asset. And so this idea of being able to scale easily just by simply, more pixels, right? 1 pixel, 2 pixels, 1 million pixels, we really don't care. And then that gives you the full coverage of the entire process, which I'll show a few examples of, and I think that will make a lot of sense. And then this last one, the visualization becomes a useful communication tool. I really want to stress this piece of it because I think a lot of people who are not familiar with the technology, might not be as aware of how this is used as a communication tool. So I always think of it as one piece, one part analysis, one part communication, because at the end of the day, you can collect, the data, whatever data you need to be able to understand how something behaves, to make a change about that asset. You can collect all the data that you want, but if you have to communicate that data to another team or another person that might not be as technical or might not be as aware of the technology or of the process or of the asset, that becomes a barrier to actually get action to be taken. And so using this as a visualization tool for communication is almost as important as the data itself, because you actually need to do something. Data without action really doesn't have a whole lot of value. So let me give you an example of one of the use cases with the idea of the full field vibration. So in a lot of instances, you need to pre-screen for sensor placement. You may need to go through and you're going to place strain gauges on an asset, right? And you think, where do I need to place these strain gauges? Even moving a strain gauge from one location to 1 inch, apart, or 1 inch, over, has a tremendous impact on the data. So you really need to understand, your game plan about how you're going to collect the data and where you need to be placing your sensors. And that can be a very, very time consuming process. By using the tool as a pre-screening to be able to understand what your asset's doing and how you need to place those sensors can have a lot of value and save a lot of time and eliminate a lot of sensors that you need to use. And I'll kind of reinforce this concept throughout the talk in some of the video demonstrations. So right now, though, what I want to do is do a live demonstration. I personally think is a live demonstration makes it easier. It sets the stage for a lot of the videos you're going to see in a lot of the case studies. One of the nice things about this demonstration is you can get an idea of the process that's involved. So any of the videos that you see, in this, you've seen so far, or you will see, this is exactly the process that it took to be able to get that, those videos collected. So let me do that real quick. And I'm going to turn on our acquisition software here, right? So I've got this little sort of motor rotor kit. These are used to train people with different technologies and measuring, vibration and things like that. So, one of the things that you have to do is you have to set your focal length of the lens, right? And you put in the distance that I use to find a laser range. I use a laser rangefinder. You can kind of see that on the screen there. Maybe on the motor there, moving around. I just get the distance that calibrates it. I put that in and you're ready to go. So I'm going to turn this on. I've got this on a little smart switch. I'm going to turn that on. Okay. So I've got that on and I am going to start taking some data. But one of the first things I want to show is kind of the speed. One of the really, really nice things about the technology is you can do it live. So I'm going to adjust the brightness just down a tad here. Get that just right. Here we go. Okay. Okay. I'm going to turn on the live amplification. So you can do this live and show that here. And if you want to actually see how that thing moves live, you can do that with the live amplification. So, one that's an interesting thing is use this as a screening tool. You can set down the tool and you can look at the asset and immediately be able to see all the motions that are present. Now, the other thing that you can do is if you need to, you can actually measure live too. So if you need to go through and make a measurement live, you can do that as well. So I can go through and turn off the live motion amplification and turn on the measurement tool and draw a box. And then that's actually going to give me a calibrated measurement of displacement. So anywhere in the scene, you can draw a box and get a measurement and a frequency spectrum. So that's actually what the asset's doing when I collected that. And that's giving me what they call a time waveform. So that's the displacement in mils calibrated. And this is the frequency spectrum. So we can see that it's running right around 20 hertz. Right? I can do that anywhere in the scene. If I wanted to move that box over here to the motor, I can do it as well. And it makes a measurement. So again, this is just, a way to be able to do things, very quickly in the field to take measurements and understand what the asset is doing. Now, the other thing too is that we can go to this standard measurement, and I'm going to take just a short 3-second video. So if I do that really quickly, I'm going to turn that off so that the motor is not running while I'm talking as much. And then I can immediately go into motion amplification. And then I can play this back and I can show you, amplify it and see all the motion. And then I can make measurements anywhere I want, right? Again, just this quick. Right. And all this data can be stored and saved and for comparison. So if you're doing like a product design, you can kind of archive this data or compare it from product to product to be able to understand it. Now, I had mentioned that there's some other things you can do with it. The displacement measurements are one of those things. But the other thing with the technology is you can do with the motion amplification videos is filter. So it's also important to understand what is occurring at different frequencies. So like in this case, we can go through and open up this filtering window and say, I would like to be able to see the motion that is associated only with the running speed, that central peak. I could do this for any one of those peaks, but I'm going to pick this one, right? And I can see that it's moving both in the X and the Y. And I can hit apply here. And that's going to go through and do filtering to only allow what's green in that spectrum. So now we're only going to show that one frequency. It's kind of going through and recalculating all the displacements. But now this is just the motion associated with the turning speed of that motor. So let's say that you had a process that was dependent on it's frequency related, and you had vibration throughout your process that was causing issue. You could relate it back to, this frequency here based on the video itself and understand how everything's moving. Let me move this to a more industrial application. So we've got a question here. It says, can you measure the RPM of the shaft? Yes, you can. So we do have a tool that you can draw a box anywhere on the shaft and it will measure the speed. And then we also have another tool called shaft inspection that allows you to go in and image the shaft. So let me just show you that really quickly. So bring this back up and I'll turn this back on. And then I'll go ahead, I already know what the shaft speed is. You could go through and measure it, but I'll just enter it in to show this other, because I think that this is interesting to kind of show. We're right around, let's see where we measured that at. Okay, so we had measured it at 20.35. So let's put that in. So if you either measure it or you know what it is, you can enter that in. I'm just converting to. I'm a Hertz person, so you know, I always have to pull out a calculator. But this is also shaft inspection too. You could measure that, but it's less interesting as a demonstration. This is a little bit more interesting in that you can actually put the camera into a different state to inspect rotating pieces of equipment or belts, you know, pulleys, any of that kind of thing by matching kind of, you know, the speed there and actually getting the camera into a different state we call shaft inspection. But it's good for any rotating equipment. Okay, I just wanted to demonstrate that with kind of along with that question about can you measure shaft speed, which you can. Okay, so let me go back to the concept of the filtering. We had just kind of left that demonstration where I filtered the rotor kit, but that's, you know, it's a little less interesting because it is, you know, single frequency that drives that. So what I want to do is I want to demonstrate this concept of filtering here. Let's see, we want, let me get up the right one. Here we go. Okay, so I want to play this back for you because there's a lot going on in this video. So play this back and speed it up a little bit. Okay. Okay, so you can kind of see that there's a screen here moving and a screen here moving, and then a screen, you know, two screens at different frequencies, and then there's a pump moving here as well, right? So let's see, I've got my amplification span changed here. You can choose what time you want to amplify. There we go. Okay, so you can see these different things moving. If I pulled up the frequency spectrum, you can see they're all at different frequencies, right? We've also had this process called what we call motion map, which is a visualization of frequency with a colorized image. So I can go through and I can actually overlay on top of this these individual motion maps at particular frequencies and highlight what's moving at that frequency. So in this case, at 15.63 Hertz, you can see it's this screen. And then at 14.02, you can see it's this screen. And then at 8.82, you can see it's the pump. Now, let me show you one of the interesting things in terms of being able to evaluate and understand your assets or your product. You know, if you notice, for example, this railing is moving, right? And that might pose a problem for you, you know, and this railing could be anything, you know, an unwanted vibration. And you notice that it's moving at this frequency and you can feel it moving when you walk there maybe. But if you look here and look at this, you notice that it highlights at that frequency too, but even, you know, more strong, you know, so it's redder under that frequency than it is under this frequency. So you can see that there's likely something going on. Intuitively, you might think, well, it's going to be the vibration of that screen right before it. But it turns out that it's more likely that this screen is coupled to it, or it has a preferred vibration at that mode. So just this idea that, you know, you can actually image this so easily across the entire field of view this quickly allows you to be able to see these vibrations. And so if you go through and turn this motion map back off, right, we could go through and filter. Now, again, watch this. You see all these screens moving, everything moving. I'm going to go through and now do something a little bit more interesting than just that, rotor kit that I showed as a demonstration. I'm going to filter for the pump, right? So I'm going to just keep that's going to keep this area inside there, right? And block everything else. So what we should get as a result is the screen should stop moving and the pump should continue to move. And again, demonstrating this is all done in real time. So there's nothing that's going on here that you wouldn't be able to do in the field. You could be right in front of this asset doing this exact same thing that I'm doing right now. There's nothing special here, nothing, that's part of the why I like to do the demonstration, because I think this tool is most used, in an industrial setting, and people need to understand, sort of what goes into it. So, okay, so now let's play this back. I'm going to amplify this, and you can see that the screens have largely stopped, with the exception of probably whatever this pump's doing to shake them. And the only thing that's moving is this pump driving this pipe work all the way through the system. You can see how much vibration it's inducing all the way through this network of pipes, all the way down through here, right? And then into the system here. So again, I just give you a short demonstration of some of the tools. There's a lot more, that goes with the technology. Again, because, really what we're doing is this full field vibration. So there's all these new ways to be able to leverage vibration in a different way, because we're extracting it from a camera. Okay. So I might return to some live demonstrations, but I'm going to go into some examples of some case studies here. Let me get PowerPoint up here, and let's see if it will behave for me. Okay, there we go. Get all the windows back up. It likes to do its own thing and sort of take over all my screens. So okay, so just give you an idea here. This is in automotive. So we're going to go through a few automotive examples just to kind of show you where you go through product design. So this has gone under testing to be able to see. This is actually induced vibration here. You can see a little bit of vibration of the wheel, but what's interesting is you can see the vibration all the way through the body when you're undergoing. So if you're doing road testing, right, simulated road testing, that sort of thing, you can actually visualize and see all the way things are interacting with each other and how they're vibrating, right? And it gives you a very quick analysis. To be able to outfit this with sensors everywhere would be very, very problematic. And again, you can do it on pretty short order with the camera, because you don't have to pick and choose where you measure. It's also really interesting because it's a lot of, you don't know what you don't know. You don't know to place sensors in certain areas. You just really might not know. Wow, I didn't know that was going. We would have never thought that. We had a group that uses it for training on vibration, and they brought it in their test lab. And the equipment they actually train on to show faults in mechanical systems had a fault in it. And they just didn't know, because they didn't know to place sensors there. So the foundation had come loose. So again, you can see the way all these systems behave. Let me show you another little bit more comprehensive. This is a car testing through revving, of the engine. We have this capability of putting vectors on the screen where you can actually you're measuring displacement, but we can graphically show the displacement, how big it is by the length of the vector, and the direction by the way it points. And so this is revving of an engine, and you can see sort of the displacement and the way it responds. One of those is a time waveform's been extracted. So here it is on the car wheel, and kind of show that. Again, just to really give an idea. The data is all there. You can pull out all the data and then also use it as a communication piece. You can see the way, what's in phase, what's out of phase, what parts are moving together, what's responding to what. When one piece moves, what is everything else doing? This is an actual sine sweep of an interior of a car through a subwoofer playing and actually vibrating and showing. So in this case, we could hear the rattle. But we didn't know where it was coming from. And when you did the sine sweep through this through this, you could actually see this console panel at the top vibrating and immediately show you exactly where the vibration is coming from. Again, you could apply the motion map to kind of hone in on that as well. So this is a case with Nissan, use it for brake testing. And so for noise, vibration, harshness group, being able to go through and actually be able to see the brakes and see what parts are moving where, in pretty short order. There's really no setup time involved, and then they can quickly get ascertain what it is that is vibrating and where, and quickly without preparation. So this is a lot of time savings and being able to understand, where the motion is in the brake during their noise, vibration, harshness testing. So this is a rivet gun. What's interesting about this is one, the failure of the part, but also the way that you can see the body shake as well. And so one of the things that's interesting, placement of this is really important, but there's also upstream and downstream vibrations that are going on too. So for example, you can actually go through, and this is all behind a light curtain, so you don't have to stop anything. You can retroactively monitor equipment like this, be able to determine, one, the vibration on those rivet guns, to be able to determine wear and tear. But second, in this case, be able to determine what else is going on, right? You can't put sensors on those body parts when during this process, right? That's like actually a piece in production, but you can actually measure it non-contact this way and see when it vibrates. Is an upstream process causing that body part to vibrate right before the rivet gun gets placed? And could staggering your timing of the different stages in that process help with that process? That's a really challenging thing to be able to do, because you can't stop the process, but anytime you can go with the camera and just simply measure it. So let's talk a little bit. So sort of some automotive examples. We'll talk a little bit about aerospace and some things like that are kind of along those lines. This is just kind of just showing a prop plane here. This was taken from quite a distance, 60 feet away, just a simple measurement, right? Nothing fancy going on here, just a demonstration that it's really easy to be able to measure things from a distance, non-contact, in a full field view. So that makes it really easy to be able to go through and do this sort of measurement. And then kind of just taking it to another one. This is helicopter, and what we've done is we've demonstrated, kind of pointed to the points of high vibration. You can still see a lot of the pieces vibrate. It's these. Needless to say, it's very important to understand what each component in this is doing, right? And so again, totally non-contact. Now, whether or not you need to go in and place sensors after this, maybe not, right? Sometimes with this technology, you can get away with finding the information, at this stage, right? Other times you think, oh man, there's a lot more vibration going on over in this area than I thought. So we might want to kind of hone in on that area and get a little bit more detail. So there's a question that came up here about the field of view. I'll play this. This one thing we can do is transient. We can actually measure transient vibration. I'll do a demonstration of that in a second, but we had a question about the field of view. I mean, this kind of gives you an idea, but there isn't really a limit on the field of view. You can use different lenses, like wide angle lenses, or back up, that if you were up against the wall, you would have a limit, but you could always go to a big field of view with, say, a wide angle lens. So that's one thing. As you move away, it does affect your resolution, but at a meter away, you can see about 0.25 microns. So if you double your distance, then it becomes 0.5 microns. And then, so at 2 meters, and you can kind of, start to get an idea of how that works. Okay. So this is a turbine engine, test cell. So that's another area that gets a lot of gets a lot of, use in this in terms of test cells, being able to outfit this in test cells. So I kind of mentioned to be able to do this continuously. So the long-term recording kind of method of doing this covers this 24/7. You could have, 3 units permanently mounted. You network them together, and they kind of communicate with each other, and they all work together to save time synchronized video data. So you could have this outfitted in a test cell with multiple cameras all measuring simultaneously. And so one question was, can you directly compare videos of the same equipment over time? Yes, you can. That's all organized like in a database that allows you to compare it. There's a video editing tool that you can do quadrants or side-by-sides of video and compare them that way. And then also the continuous monitoring solution has some of that built in as well. So just a little bit about that. If you had, I can go into details about that, maybe if you want to reach out directly or something, but in terms of being able to measure these things long-term, yes, you can. And you can compare that, and the data can all be exported out into CSV file as well. So let me show you one example on this. I'm going to go back into the software here and just show, this data set in under in real life here. Pull it up. Okay, here we go. So bring that up. So one thing is you can kind of bring up this motion map and see there's a lot of things going on here, but it allows you to really filter in, zoom in here on some of this stuff really easily and see all these things moving at different frequencies, right? And there's a lot going on in these test cells with large equipment like this, right? So here's something at 97.5 hertz. You can see some heavy vibration. So let's bring up the filtered data set for that. And this is one of those, you don't know what you don't know, right? Did you know this nozzle was moving? Maybe that's okay. Maybe that's not. Maybe that puts strain, on that. And that's not okay. In a lot of cases, it's not. But again, it's that you don't know what you don't know. And you might not have any idea that some of these pieces are moving. So be able to get this level of look at it is really where some of the power of this whole idea of full field vibration, and be able to measure that. Okay. So we'll kind of pass over that video. It just replaces the live demonstration. So component testing is another one. We mentioned the test cell, being able to go through and make measurements of product design. This is going through a series of wear and tear testing to be able to understand, what that product's going to do over time. And again, they're just inducing this, quickly to be able to measure it. And then you can visualize and watch the process the entire time to do that. And kind of talking about this whole sensor placement, you don't know what you don't know. Let's see here. Let's show this, this sort of video. This is called the observer effect, where when you actually make a measurement on something, you fundamentally change it. So you can see it with one weight, the frequency there. And then or with zero weight, but when you add a weight, say a mass, even a small mass right here, it fundamentally changes the properties of the object. So again, kind of hitting home this idea of the non-contact measurement in conjunction with testing allows you to make it more true and accurate, especially when it's a lightweight object, when there's very little weight, and you can't withstand mass loading in your testing. So just to give you an idea of how that works, there's 3 weights, and we're just fundamentally changing, the frequency, the fundamental frequency based on changing the mass. Okay. So we'll go through a couple industrial examples. This is a mining rig that they were breaking shafts on. They had no idea this was inducing a yawing, partly because it's at low frequency. And again, we're measuring displacement. So, lots of times people have accelerometers, but they don't have really great ways of making displacement measurements. And that's possible with this tool because that's the fundamental measurement. And so you can measure low frequency component things that accelerometers traditionally can't do. And that's hard for accelerometers. So it's also a good complementary tool in that case. Again, here's that motor pump combination, or the motor blower combination we showed earlier. And this is misalignment. And it's just easy to be able to see, when one side goes up, the other goes down. Those are out of phase with one another. Sometimes it looks so obvious in the videos, you wouldn't be able to see any of this with your eye. This was a facility that uses the camera in commissioning. So anytime that a new asset comes in, they tie it to their commissioning testing, and we're able to show this to the OEM to have them fix this tank. So let me show that again. And again, it's a hard conversation sometimes if you tell them the tank's doing this. When you show them the video, the conversation, you're on the same page when you show somebody a video like this to be able to explain what the problem is. So again, this is just sort of in your manufacturing. Again, that idea that you can track things, along the path. So you can look through glass if you need to, that sort of thing, and be able to track and measure the dynamic motion. Let me show something here that is, I think, in the automotive industry used a lot. This is a robot. We can actually track the motion of the robot. You can see on the top upper left, you can see the transient motion. That's the global motion of the thing. And again, this is because, we're using a camera. We're not confined to that. We're not confined to that, sensor that's just affixed to one location. And also we're, in this case, what's interesting is accelerometers and, strain gauges, that sort of thing, can't really measure bulk motion very well. Whereas with the camera as a displacement tool, you can track it all the way through the image. So we're measuring the transient path here. And then this waveform plot is the dynamic path. So that's actually the vibration that's occurring as it's moving. So it's sort of like that box that you see here that's moving with it. It's the vibration in that box. So it's measuring the dynamic properties. And then once we can get the dynamic properties as it moves, you can actually get spectral analysis. So you can actually see the frequency of vibration of that robot as it's moving through the scene. Again, so there's a lot of just coming back to this idea of the camera, taking advantage of it, taking advantage of the fact that it's non-contact, it's full field vibration. Here again is another example of being able to show, you may think this thing's in an equilibrium position and totally frozen, but it turns out that magnet's actually still pulling it and twisting it. Again, totally non-contact, and you can't really put a sensor on this to be able to measure it, is the idea. So this is the German bobsled team. They were using it from their they used this in the there to actually induce. They were in a wind tunnel and they were simulating bobsled runs, and they're just trying to get the drag down, to try to eliminate. So what they were using the camera for is actually measure the vibration under different situations to see, how streamlined is this? Where's the energy going? Is there excess vibration, going to different locations? Because that's all going to make a difference. You shift your weight just a little bit to the left or right, and it totally changes, your trajectory. And even, milliseconds could be the difference between, a gold medal. So, every little bit helps. So that's really what they're after there in trying to understand that. So just a couple more slides here. What we're showing here is the idea that acceptance testing, to go through and be able to do, we've gone through some products, household products, before with the technology, and just compared them from product to product to show what the difference is and from each one, to be able to set limits, understand what a pass fail looks like, and then actually be able to go through a series of tests with different ones. This happens to be a sander, and then knowing, you know, which one has excessive vibrations in a simple pass-fail test. And then finally, just one more slide here. We're coming up on that 10-minute mark. This is DNA, you know, so kind of just showing this, you know, very different application than all the others, but it's very interesting to be able to see the way that DNA is vibrating. And this was actually done with a microscope. So, you know, you can attach the camera to other systems to be able to look at them. I don't know if anybody in the audience is actually doing DNA testing, but, you know, if you are, here's an application for you. But interesting nonetheless. Just, you know, everything moves, and you know, we all want to understand what that motion is to either make the product better or be more efficient in our processes, or save from unplanned save downtime through understanding those processes. Okay, so I'm going to stop here. We're at the 50-minute mark, and then just take questions, and then maybe answer some here in the chat. So the first one says, let's see, we got one here. With the continuous monitoring, can you set up alarms? Yes, you can. With the continuous monitoring, you can set up alarms through contact accelerometers or 4 to 20 milliamp signals. So if you have any generic signal that you want to send to the system, it will trigger off that. You can set alarms based on, from there, it handles a general purpose IEPE sensor. So between those two, you can do pressure, you can do process signals, you can do an impact hammer, you can do velocimeters, you know, velocity probes, a whole host of things. You can use shaft RPM, so a laser tack can actually trigger it based on speeds. And then the other thing that's really interesting is what we call an ROI trigger, which is a region of interest trigger. That's really a virtual sensor. So the camera itself can monitor that location in real time and actually wait for the displacement in that box to get above a certain point or in a certain frequency spectrum to trigger an alarm, and it will save. And then once you do that, let's say you have 3 systems kind of networked together. You just plug them in on a network and they see each other. Then you can have other cameras trigger each other from that. So you can use any of the triggers from any of the cameras to trigger each other, if that makes sense. So in other words, the goal is if something happens, you get a view. If you have 3 cameras on something, all of them see it. Or if it's a process, right? You've got station A, B, and C. They're all working to create one thing, but they impact each other. You can trigger that way as well. Yeah. So next question is, the camera would be affected. Yeah, that's true. So we have 2 ways of taking care of, well, really 3. You know, we always recommend sometimes just moving a few feet away really dampens the vibrations, especially in things like test cells where they're actually isolated. But so we always recommend, you know, you can move away, you can double your distance and then change the lens to a zoom lens to totally accommodate that distance change from you to the object. So that's one recommendation. We also have vibration pads that go underneath that absorb and isolate a lot of that vibration to keep it from getting to the camera. And then finally, we have a stabilization software that actually goes through. And so when the camera moves, it really leaves a signature, a really distinct signature in the data. Really what happens is everything moves together, right? So if the camera moves, so we can actually extract that out and get rid of that and then take it out of the video. And then one more way is filtering. So if the floor vibration's at 10 Hertz and you're interested in 20 Hertz, then you can actually just filter out the floor vibration or just filter for the 20 Hertz and it eliminates the floor vibration. So lots of ways to do that. We have a lot of people using it in mining industry. So that's probably the worst case scenario, I think, and with great success. So dust in a production environment, dust, weld, sparks. Yeah. We've been in lots of those. I mean, we're in, you know, lots of steel facilities, lots of manufacturing. I mean, we run the gambit of those. So it does well. I mean, you know, if it gets to the point where you can't see it, like the steam is so much that you actually can't see it, then that's problematic. But, you know, dust and weld sparks and things like that, you can kind of filter a lot of that out. But in a lot of cases, it doesn't actually keep you from being able to measure that. So we are, for example, we're in a lot of pulp and paper, that sort of environment. So that's, I think, okay. Any other questions? I mean, you feel free to, I don't know if everybody's muted automatically or.
Hey, Jeff, this is Frank. I think one of them was already addressed, but it was questioning, will this presentation be available online afterwards? And the answer is yes, I believe on the SAE Atlanta website.
Yeah. Okay. And then another one just came in and says, what does training look like? Yeah. So it's interesting. One of the interesting things about this was the newness in some level to this technology is the photography element. Just learning, you know, how does, you know, swapping out a lens change? How does changing your aperture affect your data? And so, yes, there is training all the way from basic to advanced. You know, you can do 3 days training on the technology, even at your facility, and it covers all the way from learning about the camera, learning about how to take data to real life data collection on assets. So 3 days from beginning to end. And then there's an advanced training that you can go through to be able to do even more, you know, once you get some experience under your belt, and then you come back and you can kind of learn advanced techniques. So any other questions? Well, if one thing I would just want to say is I do appreciate everybody taking the time out. I know that, you know, everybody's time's valuable, and, you know, taking an hour out of the day is not always easy. So I do appreciate you taking the time out. I put up some contact information there. Feel free to send me an email if you're just interested. I mean, you know, I like talking about the technology. I'm happy to talk about it at any time. My contact information's there, LinkedIn, feel free. We've got a lot of videos on the YouTube page. You know, you can go there, you know, pop some popcorn. We got, you know, hundreds, if not thousands of videos there. You can just, you know, create a playlist if you want, you know, to do that. And see, it looks like we got one more question. Are we involved in aerospace design and development testing? Yes. So, I mean, you know, test cells, that sort of thing. People use the technology for a broad range of things. So you can kind of imagine all the things that you saw here today. You can kind of imagine some of the applications. And new vehicle design. Yes. I mean, the brake example was one. Yes. And new vehicle design for aerospace. Yes. Probably one I can mention that does use the technology is NASA. So we're in several NASA facilities. NASA JPL uses it for aerospace product design. So in new vehicles too, that haven't gone up in space yet.
And then Jeff, you do have a newsletter, is that correct? How do people sign up for your newsletter if they'd like to?
Yeah, so you can go to our website, and there's a sign up page there to be able to sign up for the newsletter. I think that's you. Yeah, probably should have that on the slide, but you can tell I'm not necessarily a salesy salesman type person. But yeah, you can sign up on our newsletter at our website.
Thank you so much for the presentation, Jeff. It was very, very interesting. We are so happy you were able to speak to everybody today.
Thanks, Heather.
Okay, we've come to the close of our time here at our Lunch and Learn. Yes, just to echo what Heather said, Dr. Hay, thank you so much for your impressive presentation. The application of this technology seems like it just has endless uses in product design and R&D and product testing and problem solving and quality testing, vehicle verification. The endless uses just go on and on. So I think motion application has a big future. But we're very thankful that you were here today and answered a lot of questions. Like we said before, the recording of this will be at our SAE website, and I hope people will sign up for your newsletter as well. So just to close this out, for all the participants, we say thank you for joining us for Lunch and Learn. We hope that we'll have more offerings in the very near future for you with other compelling topics. Thank you to Heather and Mike and the SAE members that joined today, all of the board for helping us put this together. And we want you to stay connected through our SAE Atlanta newsletter for future events. Go to the homepage at www.saeatlanta.org. Provide us with your name and your email address so that we can stay in contact. So that brings us to the conclusion of our meeting. Yeah, thank you, Heather, for putting that slide up there. Just a quick slide that you'll see from our Atlanta newsletter. Again, it's got the website there and some of our great sponsors that we have. And we urge you to stay contacted and stay connected with SAE Atlanta. There's a way to contact us through the website if you have any additional questions about the presentation or about SAE Atlanta. So thank you again, everyone. And this concludes our meeting for today. Hope you'll join us next time at our next Lunch and Learn. Thank you.